Hello, 6th grade. This is going to be part 1 of your 1.2 and 1.3 notes for this section entitled Earth and Space. So this is going to be, primarily should be somewhat of a review for some of you. A lot of this stuff I'm just going to kind of move through. You can use this PowerPoint. I'll have the link to the YouTube link that is the talk through, but I'll also have the download for the PowerPoint for you to view as well, for you to click through at your own pace. So before we begin, I would like you to ask yourself, what is different about these pictures and what is the same? So I'll give you a chance to think out loud and talk. You can pause the video. Okay, so you obviously probably were like, they're both wearing red. Yes, they are. Very good. Very astute. Okay, so they are both wearing red. And they both appeared to be celebrating or in the middle of some type of season. All right, the one on the left is clearly in the wintertime, and the one on the right is clearly in the summertime? Well, I'm going to put a bookmark in this, all right? So don't forget about this picture. We're going to talk about it in just a little bit, okay? So just because now Christmas is on my mind, we do have a nice little song. I know, it's super appropriate because it's March. Okay, our key concept is Earth moves in space in two major ways. So we're going to talk about Earth moving in space. Alright, so believe it or not, those pictures are going to come back and they're going to have a purpose. So Earth moves in space in two major ways, rotation and revolution. Does anybody know what song this is? Yes, God rest you, Mary Jefferson. Very good. All right, so we're going to first talk about rotation. And in order to understand our rotation, we have to understand how the Earth is divided. So the Earth is divided up with imaginary lines. And you were taught this by Mr. Flynn, and we have also talked about this too when we were talking about mapping the Earth's surface and things like that. So the imaginary line that passed through Earth's center and the north and south poles is Earth's axis, north and south. And the imaginary line that passes through the Earth going east and west is called, very good, the equator. And it divides it east and west. All right, so Earth's rotation, the spinning of Earth's on its axis is called its rotation. Unfortunately, you can't talk to your table partner. You're going to have to talk to your mom, your dad, your brother, your sister, your dog, your stuffed animal about the following question. So this should be a review because we just went over this in 1.1. As Earth rotates eastward, which way does the sun appear to move? It would appear to move west. And take a look at this picture. It does a really good job of showing that as we spin in this direction, see my mouse going to the quote-unquote right, all right, the sun appears to quote-unquote move left, all right? You can see that, and just think of it this way. We experience nighttime on the eastern seaboard before the western coast, okay? The east coast gets nighttime first versus the west coast, all right? So rotation, again, our Earth is spinning in that direction. How long does it take for the Earth to rotate once? Womp womp. It takes just under 24 hours. Sorry. It takes about 23 hours and 56 minutes, but we round up to make it 24 and get our days. All right, does anybody know how fast the Earth is actually rotating? Wow, very impressive. Yes, you are on point. 1,037 miles per hour or 1,670 kilometers per hour. All right, so if you are following along in your notes, you should be up to number 7 at this point. All right, we're going to move into Earth. So we just talked about Earth's rotation, spinning on its axis, all right, imaginary axis, and spinning on that. And then we need to talk about revolution. So revolution, all right, a revolution is a sudden, radical, or complete change, especially the overthrow or renunciation of one government or ruler and the substitution of another by the governed. Oh, yes, I know. No, that's okay. You can keep laughing. I'll wait. Yes. Thank you. Okay, sorry. We got to move on. We got to stay on task. Haha. So, Earth's revolution. A revolution is defined as the movement of one object around another. All right. And in this case, Earth revolves around the Hooray! It's not the moon, it's the sun. So it evolves around the sun. The path Earth takes is called its orbit, and the Earth travels in an elliptical pattern, which looks like this. And this is what you're going to draw. All right, the Earth travels in an ellipse, which looks like this. It is not, okay, an ellipse is not a circle. All right, it's not a perfect circle. Earth's elliptical orbit is going to influence several things of how we experience several things on Earth. Now, if you look at this, it's not going to be when we're closer to the sun, it's hotter, and when we're farther away, it's cooler. That's not how it works, all right? I'm sorry to dismantle that thought pattern, but that is not how that works. We're going to touch upon what influences Earth's seasons momentarily. But before we get into that, just to kind of talk about time scales and years and things like that, I'm going to talk to you about something you've never heard of. Who can tell me what a calendar is? Nice. Calendars tell us days, months, years, and help us to organize our lives. They look like this. You all use them so much when you use your assignment books, and I know some of you are like, whoa, 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 whoa. Slow down there, fella. Going too fast. All right, so a calendar is basically just a brief history of those calendars. Egyptians observed star motions and made the year 365 days, which is pretty impressive for them to have come up with that so long ago. And they came up with 12 months with 30 days each, extra 5 at the end. The Romans then calculated it takes about 365 and a quarter days. So every 4 years we have what we had this year is a leap year. So it takes about 365 and a quarter days to get around. So after 4 years, we put that together and we come up with our extra day on February 29th. And then Pope Gregory the 13th made some changes, and that's the one we use today, called the Gregorian calendar. All right. So let's talk about seasons. So there are several things that cause seasons. There are 2 factors. The first is Earth's tilt on its axis. So you can see this tilt. All right. Earth has this tilt on its axis and its position relative to the sun. Now, that does not mean when it's closer to the sun, when it's farther away from the sun. It has to do with the way the light is hitting the sun. Or excuse me, the light is hitting the Earth. And I'm going to show you that momentarily. So in March and September, our northern hemisphere is tilted in neither direction and gives us spring or fall. We are dead on with the sun. And give me a minute, because you're not going to don't fill out your chart yet. I actually filled the chart out for you, and then I'm going to show you some pictures, because I know this can be kind of confusing if I'm just talking to you, but I'll show you some pictures momentarily. In June, the northern hemisphere is tilted towards and gives us summer. In December, the northern hemisphere is tilted away and gives us winter. These are all called solstices. Solstices, solstices. Okay, so we actually just went through these 2 are solstices, these are equinox or autumnal or vernal equinox. So this was just our vernal equinox in March. We just had that, where we had equal amount of day and light, 12 hours each. In June and December, in June, in the summer solstice, we're going to have more sunlight. In the winter solstice, you have more or less sunlight. So chart for your notes, so you can pause this. I'm not going to read this whole thing for it. Well, yes, I will. All right, I will. So the northern hemisphere tilts up and down normally, and I'm going to show you what that means in a second. So for March, it's up and down, and it's spring. In June, the northern hemisphere towards the sun, and that's summer. In September, up and down in the fall, and December, northern hemisphere is away from the sun in the wintertime. So take a look. All right, if we zoom in right here, all right, this is going to be, we're going to look at this one right here. So I blocked out these. So we're going to look at this one up here. And this is what I'm talking about when I say dead on. So you can see that there's no tilt. There is still a tilt, but it's not every part of the Earth is getting equal amounts. But when we're on this side, you can see that they're going to get different amounts of sunlight. And this one, there's no way, excuse me, the spring equinox is right here. All right, the spring equinox is here. We're going to look at the summer solstice next, which one on the left, right, or bottom is going to be the summer solstice. Think about the summer solstice needing the northern hemisphere to be tilted towards the sun. That would be, bingo, the one on the left. That would be our summer solstice, okay? You're going to see the sun's rays are hitting it right on, straight on, and the southern hemisphere is not getting as direct of rays. Then your autumnal equinox is going to be down here. I guess I forgot to wipe it out. Sorry about that. The autumnal equinox, again, that's dead on. And then your winter solstice is going to be over here. You can see once again that the sunlight is hitting the bottom part of the southern hemisphere more accurately, if you can If you have any questions on that, please let me know. All right, and then once again, see, it doesn't have to do with our distance because you can see we are actually farther away from the sun in winter and summer than we are in autumn and spring, technically speaking. So you can see that we are moving away in our elliptical orbit September, August, July, but then our northern hemisphere is getting hit June, May, and April. Then it's dead on in Oh, I guess I was going backwards. Sorry. July, August, September, and autumn. Then October, November, December in the bottom of the southern hemisphere. Then January, February, March into spring, getting that. And then April, May, and June hitting the northern hemisphere. So the solstice, which we just talked about, I'll just kind of pass through this because I just talked about that. Our equinox, once again, you can pause this video if you need to see that. And so once again, let's compare these. So here's where I can change this for you. All right. So on the left, this would be in the northern hemisphere. On the right, this would be in the southern hemisphere. They're technically both in December. That is the case because in the northern hemisphere in December, it's wintertime. In the southern hemisphere in December, it is summertime. So even though we talked all about this being winter for us, it's flipped. So this would be summer for the southern hemisphere and winter for the southern hemisphere there. So these pictures are different but the same. So they are both celebrating Christmas just in different styles. Yes, in Australia and Africa and parts of Africa and South America and things like that, they experience Christmas in the summer. Okay, so that's going to end our notes for 1.2. We're going to get into 1.3, gravity and motion, in the next video. Thank you for watching.